right, so in this one, we're going to talk about non-uniform circular motion. That means my speed is increasing or decreasing as I go around a circle. So as a reminder, when we started talking about circular motion, we learned that there are really two types of acceleration. There's the part that controls speed. We call that one translational acceleration. And we said that's called AT, and that's my translational acceleration, and it's in charge of speed. We spent most of our time talking about centripetal acceleration, which is in charge of direction. So uniform circular motion only has centripetal acceleration because the speed is staying the same as I go around the circle. So on my circle, when I'm right here and my velocity is going this way, I experience a centripetal acceleration going straight down, right? That keeps me moving in circular motion. Now, if I have non-uniform circular motion and I'm speeding up, translational acceleration, in order for it to work, would have to be in the same direction as my velocity. Or if I'm slowing down, the opposite direction of my velocity, right? Centripetal acceleration is determining velocity, not change in direction. So it has to be in the same direction as my velocity. As I go around the circle, AT is in the same direction or the opposite direction of my translational velocity. Again, if it's in any other direction, then it'll be partially responsible for centripetal acceleration instead. So it has to be the component of acceleration that's going with my velocity or against it. That would speed me up or slow me down, right? That makes sense. So if I have centripetal acceleration, that's fine. I go in a circle at constant speed. If I have translational acceleration, I'm going to speed up or slow down. So centripetal acceleration and translational acceleration combine to be this total acceleration. So when you see A, what that would be a total acceleration if it's an object moving in circular motion, and it would be a combination of the translational and the centripetal. It would have a direction equal to the inverse tangent of, let's see, if I want the angle away from the translational component, then that would be my adjacent, so it'd be AC over AT. Really not asked for that very often. You might be able to draw a picture of it, but you should know that A is always between AT and AC. That's always the truth. It's going to be between the two because it's a combination of them. It's the vector sum, it's the resultant vector of my two types of acceleration. So this is us learning, all right? If I have non-circular motion, that means I'm going to have some translational acceleration on top of my centripetal acceleration. Now here's the dealio. If I'm speeding up, as a reminder, my amount of centripetal acceleration hasn't changed. AC is equal to V squared over R. So V is increasing and my centripetal acceleration is staying the same. Let's say it's just gravity and I'm a satellite orbiting the Earth, right? The force of gravity didn't change, sorry, but I'm speeding up. So if I speed up, the radius of my circle would have to get bigger. So if I'm experiencing this, I'm probably going to also experience an increase in my radius of the circle as I speed up. If I'm slowing down, well now my velocity is slowing down, my centripetal acceleration stays the same, so my radius has to go down. So if I was slowing down and my translational acceleration was the opposite direction, I would probably see myself spiraling inward, okay? Keep that in mind, all right? Let's talk one more thing. How do I get the angular components to work with these components? So what about angular acceleration? Angular acceleration is the friend of this one. So these guys are the same thing, angular acceleration, which we call the fish in alpha. I call it the fish. Angular acceleration is this, and it equals W squared. No. It equals, sorry, a change in W over time. I don't know what I'm doing. Change in W over a change in time. It's the change in angular velocity over time. Angular velocity is directly related to the speed that I'm going. So if I change my angular velocity, I'm going to change my translational velocity if my radius stays the same. So angular acceleration is related to translational acceleration. These are the same thing because they're both in charge of a change in speed. So those two go together. That's my angular acceleration. It's a change in angular velocity over a change in time. These two are responsible for speed. They're not responsible for direction, so we know how these ones work. These both follow our kinematic equations. I can do them either with the angular or the translational information. So what I mean by that is that AT is responsible for speeding up and slowing down. So it was the acceleration we used in these kinematic equations. When we said that V final is equal to V initial plus AT, that was translational. When we said delta X is equal to V naught T plus 1/2 AT squared, that was translational acceleration. When we said V squared equals V naught squared plus 2A delta X. These same kinematic equations apply to angular acceleration and velocity and distance. So I would have final angular velocity, initial angular velocity, alpha t. I would have change in theta is equal to initial alpha t squared. And then final angular is equal to initial angular plus 2 alpha delta theta. That's how closely related angular acceleration and translational acceleration are. They are the same thing. If I'm speeding up as I go faster around a circle, that means I'm speeding up my translational velocity because I'm going further distance in the same amount of time. So these translational equations work. If I'm given translational information, it went a distance of this in a certain amount of time, that's great. If instead the question says it was going at 2,400 RPM and now it's going at 3,000 RPM, it had an angular acceleration of blank revs per second squared. How long did that take? I can figure it out. I can use the original kinematic equations to do this. This is not something you have to do very often, but I just want to keep you in the loop as a reminder to go back and forth between these things. V is equal to WR and theta R is equal to delta X. So that's a way I can go between translational and angular if I need to. All right, that's all I have. So if I have non-uniform circular motion, that means I'm speeding up as I go in a circle. If I'm not careful and I'm not changing the force applied, my centripetal acceleration stay the same, so I'm probably gonna have to change the radius of that circle as I either speed up or slow down, right? Now, it's translational acceleration that's in charge of speed. So if I'm speeding up or slowing down, I'm gonna have translational acceleration. Translational acceleration is equal to, or goes with, angular acceleration, which would be the increase in angular velocity over time. That change in angular velocity over time is angular acceleration and would still lead to a change in speed. If I'm going at a faster angular velocity, I'm going at a faster speed because I'm covering more distance in the same amount of time. The trick is, as I go faster, I have to watch out for what my centripetal acceleration does. If it doesn't change, then I'm probably gonna have to change the radius of my circle to go with it. And then I can go between these two. Both of them use the kinematic equations, and I can go between the two with this over here. All right, that's all.